Hello everyone, and welcome back to this series on single variable calculus, and today we're going to be talking about a very important method of integration known as improper integration. Up to this point, we've pretty much assumed that the function that we're integrating is well behaved. Moreover, we've been assuming it's at least continuous on some closed interval ab, where both a and b are finite real numbers. And if this is indeed the case, then the fundamental theorem of calculus states that the area underneath f, or bounded by f in the x-axis, on the interval ab is just equal to capital F of b minus capital F of a, where the derivative of capital F is equal to little f, or capital F is the antiderivative, any one of them is fine, of the little function f. So a natural question comes here. What if the function is not continuous on a, b, and or a and b, one of them or both, are not finite? So if this is the case, then what we have is an improper integral. So how are we going to handle improper integrals? So we have a few different types that we want to sort of organize this into. So the first type, for which I'm just going to call type 1, and these aren't in any special order, I'm just calling them type 1, type 2, and type 3. So the first one says the following. So let's suppose that a and b are both finite numbers, and let's assume that f is, let's say it contains a removable or a jump discontinuity. At some point, let's say 1 point, x is equal to c, where a is less than c is less than b. So c is between a and b, for which it is either a removable or jump discontinuity. Keep in mind we also have infinite discontinuities, but we'll deal with that at a different time. So let's just draw a little picture to sort of see what's going on here. So we have a here, we have b here, and we have some point c here as well. And what's going on at this point c is either a removable or a jump discontinuity. Let's do a jump discontinuity just to make it a little bit more fun. And then we have the function doing some stuff outside this interval, who knows what and who cares. So obviously the area underneath this curve, so the integral from a to b of f of x, isn't defined with respect to the fundamental theorem of calculus. You can't do capital F of b minus capital F of a because f is not continuous on ab, so it doesn't apply. But what are we actually looking for? Well, we're looking for the area underneath this curve from a to b, which is technically speaking everything from a to c, everything from c to b, and add it up. And that's precisely how we're going to be defining this improper integral. So we're going to define this to be equal to the integral from a to b, or the integral from a to c rather, dx, plus the integral from c to b of f of x dx. That is, we're going to find this first area here, we're going to call it area A, and then we're going to find this area here, we're going to call that area B, and then the area from A to B will just be A plus B. So that's how we're going to define this particular type of improper integral. That is, we have a removable or jump discontinuity on the interior of our integral domain. So let's actually work through an example on how to use this. So our first example. Suppose we have some function f of x which is equal to 3x squared for x less than 1, and let's do 2x plus 1 for x bigger than 1. So if we take the limit as x approaches 1 from the left, we're going to get 3. From the right, we're going to get 2 plus 1, which is also 3. So we definitely do have a removable discontinuity for this particular function. So we have a removable discontinuity at x is equal to 1. So if we plan to integrate from something less than 1 to something bigger than 1, then we have to use this decomposition that we just derived. For example, let's assume that we want the integral from 2 to 3 of this function. So by our definition of the type 1 improper integral, this is just going to be equal to the integral from minus 2 to 1 of f of x plus the integral from 1 to 3 of f of x dx, right? Where this 1 is the removable, or potentially a jump, discontinuity for this function. Now we can use the definition of our piecewise function to evaluate this integral, because this is just going to be equal to the integral from minus 2 to 1 of 3x squared dx, and then the integral from 1 to 3 of 2x plus 1 dx. And then, since 3x squared and 2x plus 1 are continuous on their associated interval, then we can apply the fundamental theorem of calculus on each of them and then add. So what is that going to be? So the antiderivative of 3x squared we know is going to be equal to x cubed. And then we need to evaluate that at 1 and then at minus 2. And then the antiderivative of 2x plus 1, that's going to be x squared plus x. And then we need to evaluate that at 3 and then 1 and then subtract. So what is that going to give us? So x cubed is going to evaluate to 1, minus 2 cubed is going to be evaluated at minus 8. And then for this, we're going to have 3 squared, which is 9, plus 3, which is 12. And then minus 1 squared is 1, plus 1 is going to be 2, so that's going to be subtracted by 2. So that means the integral from minus 2 to 3 of our original function is just going to be equal to 1 minus negative 8, that's going to be equal to 9, plus 12 minus 2, that's going to be equal to 10, giving us a final answer of 19. Right? So that's how we can solve type 1 improper integrals. Now let's look at a different type of improper integral. Again, let's assume that our bounds are both finite, i.e. a and b are real numbers. Let's assume that f is continuous on the inside of AB, but not at the boundaries. And let's assume that f contains an infinite discontinuity at either x equals a and or x equals b. Right? So we have a couple cases here, right? So we can have a vertical asymptote at x is equal to a. We could have a vertical asymptote at x is equal to b. Or we could have a vertical asymptote at x is equal to a and also x is equal to b. And then we have our function doing its own thing on this interval, right? So we could have this, we could have something like that, or we could have something like that, right? So continuous on the open interval, but vertical asymptote on the left, right, or both. So how are we going to go about defining each of these three different types of improper integrals? So what we're going to do is we're going to pick some points either shortly after or shortly before the vertical asymptotes. So for example, here we're going to choose the number a plus epsilon, and then we're going to find the associated area here, which is going to depend on epsilon. And then what we're going to do is we're going to take this number, a plus epsilon, and send epsilon to 0, and then this area will eventually collapse to that vertical asymptote. Similar, we're going to choose a number here, b minus epsilon, where epsilon's a positive number. We're going to find the area underneath here, and then we're going to send that area to the right by sending epsilon to 0. And for the two-sided case, we're going to be choosing two numbers, a plus epsilon and b minus epsilon, finding the area between both of them because it will be continuous by assumption. And then we're going to send both of those boundaries to their associated vertical asymptotes and hope that that associated integral exists. And if it doesn't exist under the limit, then we say that that integral is going to diverge. So if we write this in formal notation, so this first picture is going to be the integral from a to b of f of x dx. This is going to be defined to be equal to the limit as epsilon approaches 0 from the right of the integral of a plus epsilon to b of f of x dx. The next one, the integral from a to b of f of x dx, this will be defined to be the limit as epsilon approaches 0 from the right of the integral from a to b minus epsilon of f of x dx. And the last, the integral from a to b of f of x dx, if you have vertical asymptotes at a and b, will be defined to be equal to the limit as epsilon approaches 0 from the right of a plus epsilon b minus epsilon of f of x dx. Right? So those are our three different types. Now let's work through an example to demonstrate how to use these new definitions. Let's assume that we're interested in finding the integral from 0 to 1 of 1 over x times 1 minus x. So it's very easy to see that this function is a rational function with vertical asymptotes located at x is equal to 0 and x is equal to 1, and it's going to be continuous everywhere inside of it. In particular, if we choose some epsilon that's arbitrarily small but positive, pick a number here, which is 0 plus epsilon, pick a number here, which is 1 minus epsilon, then it's very easy to see that our function is continuous here. Right? So regardless of what this function looks like, we can always find the area underneath this curve on that bound, and then send that area to 0 and 1 from both sides at equal rates, and hopefully that area will converge. So let's see how that's going to be done. So by definition, this will be equal to the limit as epsilon approaches 0 from the right of, so 0 plus epsilon, that's just going to be equal to epsilon, and then we have 1 minus epsilon on the top, and then we're going to have dx divided by x times 1 minus x. If you want to continue this problem on your own, feel free to pause the video and see if you get the right answer or the same answer as me. So what we're going to do for this integrand is we're going to do partial fraction decomposition on this. So partial fraction decomposition. And you should be able to find that that's going to be equivalent to, what would that be? Let's actually switch this into x minus 1. You'll get the same answer, just a negative sign in the front. So this is going to be equal to 1 over x minus 1 minus 1 over x. Or if you kept in the original orientation, a minus 1, or 1 minus x minus 1 over x minus 1. So once we have this via partial fraction decomposition, then we can just integrate each of these terms because this function is continuous on epsilon to 1 minus epsilon, where epsilon is an arbitrarily small but positive number. So this is going to be equal to what? So this is going to be the limit as epsilon approaches 0 from the right of the natural log of the absolute value of x minus 1. Important, don't forget your absolute value on the natural log interior. And then we're going to have the natural log of x here. And then we need to evaluate this as x approaches 1 minus epsilon and as x approaches epsilon. Before I substitute, I just want to simplify this just a little bit. And this is going to be equal to the limit as epsilon goes to 0 from the right of the natural log of the absolute value of x minus 1 over x. All right, and keep in mind this still needs to be evaluated as x goes to 1 minus epsilon and as x goes to epsilon. Now let's evaluate upper limit, lower limit, and subtract. So that will be equal to what? So limit epsilon goes to 0 from the right of the natural log of 1 minus epsilon minus 1 all over 1 minus epsilon, and keep in mind absolute values are still there, minus the natural log of epsilon minus 1 over epsilon. Now let's clean this up just a little bit before we evaluate the limit. So we have the limit, epsilon approaches 0 from the right. 1 minus 1, that's going to be equal to 0. And then we're going to have minus epsilon on the inside. So minus epsilon all over 1 minus epsilon. And then over here we have natural log of epsilon minus 1 over epsilon. So what I'm going to do now is just to take the absolute value and just do some properties of logarithms, because we have the natural log of a minus the natural log of b, which is the same as natural log of a divided by b. In that fraction, we can multiply by the reciprocal. So this is going to be equal to the limit as epsilon approaches 0 from the right of the natural log. Let's do epsilon over epsilon minus 1 for the first, because when you take the absolute value, it doesn't really matter the order of subtraction. And then what we're going to do is multiply this by the reciprocal of that one, which will be epsilon over epsilon minus 1. So once we have this, notice that this is the same as the limit of epsilon goes to 0 of the natural log of epsilon squared over epsilon minus 1 squared, and that squared can go in front of the natural log by properties of logarithms. So now what we have here is our integral that we started with, 0 to 1, of x times x minus 1 is equal to 2 times the limit as epsilon goes to 0 from the right of the natural log of epsilon all over epsilon minus 1. Right, and let's throw in our absolute values there. So once we have this, and I actually want to reverse my bottom again, back to 1 minus epsilon. You'll see why I prefer this in a moment. We'll make this next statement clearer. Once you have this, what do we have? So let's plug in 0. So this is going to be equal to 2 times, so plug in 0, so that's going to be some number arbitrarily close to 0 from the right, over 1 minus some number really close to 0 from the right, and 1 minus 0 plus, we know that's just going to be equal to 1 plus, and 0 plus divided by 1 plus, that's just going to be equal to 0 plus. So we have 2 times the natural log of 0 plus, and we know the natural log of 0 plus is positive infinity, and positive infinity times 2 is equal to positive infinity. So obviously this number does not belong in the set of reals, so that means the integral does not converge. Right. So that's a sad day for this integral, but no worries. Not all improper integrals converge, but some do, as the first one we actually did converge to something. The third type of improper integral that we're going to discuss is when one or both of the bounds are infinite. So we obviously have three cases. The left boundary is infinite, the right boundary is infinite, and both are infinite. So the integral from a to infinity, where a is a finite number and infinity is either an infinite quantity, is going to be defined as follows. So we're going to define this as the limit as m goes to infinity, but you can use some other letter if you prefer it, of the integral from a to m of f of x dx. Right? Obviously, if it's continuous on a infinity in this case, it's obviously going to be continuous on a to m, so this is going to be well defined. And this next one is going to be defined to be equal to the limit as m goes to infinity, not negative infinity, but you could, I guess, of minus m to b of f of x dx. And this last one defined in a similar fashion, we're going to do the limit as capital M goes to infinity of minus m to m of f of x dx. Right? So those three cases of this particular type of improper integral. So now that we have the definitions, let's actually work through an example to sort of see how they work. So let's take a fun example. Let's do the integral from minus infinity to infinity, since it has both, of e to the power minus absolute value of x dx. Now there's a couple of things you can start this integral off with, but I'm going to start off by observing that this function is an even function. And if you don't remember what an even function is, that means f of x equals f of minus x for all x and inside of that domain. Graphically speaking, this function is symmetric about the y-axis. So that means in this particular picture that I'm sketching, the teal region and the green region have the same exact area. So what we can do is we can take this integral and say, oh, that's just 2 times the integral from 0 to infinity of e to the power minus positive x, because x is a positive number and the absolute value of a positive number is itself, dx. Right? So now that we have this, now we can just be like, oh, I know how to define that. That's just going to be 2 times the limit as m goes to infinity of the integral from 0 to m e to the minus x dx. And I already know how to deal with that because that's continuous on the interval 0 to m. So the antiderivative of e to the minus x is negative e to the minus x. So I'll just factor that negative sign out just so I don't forget it. So minus 2 times the limit as m goes to infinity of e to the minus x, and now we need to evaluate that as x goes to m and as x goes to 0. So this is going to be equal to what? So that's going to be equal to minus 2 times the limit as m goes to infinity of e to the minus m minus e to the minus 0. That's just going to be equal to 1. Now we can evaluate this limit, and that's going to be equal to what? So that's going to be minus 2 times, that's going to go to 0 minus 1, and then the overall integral will be 2. Right? So therefore, we can conclude that the integral from minus infinity to infinity of e to the minus the absolute value of x dx will just be equal to 2. Right? So that's actually a quite nice integral to practice with. There's just one more point that I want to make about improper integrals. Let's assume that we have some number in between a and b, such as c, and let's assume that the integral from a to b of f is improper with either the integral from a to c of f and or the integral from c to b is divergent. Keep in mind, we've already considered the case where c is a removable or jump discontinuity. So this pretty much only applies where you have an infinite discontinuity in between a and b located at c. Then we will also say that if the integral from a to c of f or the integral from c to b is divergent, then that integral of f is also divergent as well. But just because it's divergent, it doesn't mean you can't assign a particular value that is meaningful to this divergent integral. So if this improper integral does happen to converge under the limit definition of the improper integral associated to it, then we say that its limiting value is what we call the principal value of the integral and will be denoted by PV integral AB of f. Let's just take a very basic example to illustrate this idea. So let's assume that we have the integral from minus 3 to 2 of 1 over x dx. It's very easy to see that from the graph of 1 over x, this function is definitely symmetric about the origin, so one could conjecture that the integral from minus infinity to infinity underneath 1 over x should be 0, because this area, even if infinite, must be equal to this area here, 1 positive, 1 negative, so it should net out to 0. But if we integrate from minus infinity to 0, that's infinite, and hence the integral is divergent. So this is a divergent integral, right? But even if it is, you shouldn't be able to say it's divergent based upon just looking at this. You have to be able to decompose it in such a way that the decomposition produces one or two, or potentially infinitely many, divergent integrals, right? So how are we going to do that? Well, obviously there's a point in between minus 3 and 2 for this function where there is an issue, right? Because if we look at our domain, minus 3 and positive 2, there's an issue located at 0. So we have to break this integral into two pieces, minus 3 to 0 and 0 to 2. Once we do that, we're going to have what? So that's going to be equal to the integral from minus 3 to 0 of 1 over x dx plus the integral from 0 to 2 of 1 over x dx. Now what do you have? Now you have a vertical asymptote on the right boundary of the first integral, and you have a vertical asymptote on the left boundary of the second integral. So once you apply the definition on each of them, what you're going to see is that both of these integrals are divergent, right? But what we can do, since those points are technically connected, is we can combine their limits together. Because what is this? Well, this is precisely or equivalently equal to the limit as epsilon approaches 0 from the right. So we can choose this number 0 minus epsilon and this number 0 minus epsilon, calculate the area underneath both of them and squeeze them together, and hopefully it converges. So once you have this, because since this integral is divergent, maybe we can get a principal value for this integral. So let's see if it exists anyway. So this is going to be equal to the limit as epsilon goes to 0 of minus 3 to 0 minus epsilon of 1 over x dx, and then plus the integral from 0 plus epsilon to 2 of 1 over x dx, and both of these integrals are defined. Now it doesn't necessarily mean the limit will be defined either, as we saw before, but let's just see what happens. So let's see what happens here. So this is going to be equal to the limit as epsilon approaches 0 from the right of what? So the antiderivatives of our 1 over x's are going to be the natural log of x. So we're going to have the natural log of minus epsilon minus the natural log of the absolute value of negative 3. So that's going to be our first. And then we're going to have the natural log of the absolute value of 2 minus the natural log of our epsilon. So that's going to be our second integral. And let's just take our absolute values of our interiors and let's just see what happens here. So limit as epsilon goes to 0 from the right. So natural log of epsilon, that's just going to be equal to the natural log of epsilon. Epsilon's a positive number, keep in mind. And then we have the natural log of 3. And then we have the natural log of 2. And then we have the natural log of epsilon over here. But notice before we take our limits, we have that removable discontinuity, or I guess you could say a removable infinite discontinuity with respect to our Riemann integral, which is actually pretty interesting. And then we're going to be left with something that doesn't have anything to do with epsilon at all, so our epsilon sort of is irrelevant. So we just have the natural log of 2 minus the natural log of 3, which by properties of natural log is just going to be the natural log of 2/3, right? So this is under the limit in terms of the value of the whole improper integral. Therefore, we say that the principal value of the integral from minus 3 to 2 of 1 over x dx is equal to 2 over 3, the natural log. Or you could also say, and you would be equally correct, say the integral from minus 3 to 2 of 1 over x without the principal value is divergent. Right? So that's one way you can assign values to integrals that are divergent, but keep in mind, not all divergent integrals have principal values, but if an integral does converge, the principal value is the same as the value for which the integral converges to. Fun little theorem to prove. Anyway, those are some of the basics that you definitely should know with working with improper integrals. Hope to see you in the next video, and I hope you enjoyed this one. Take care.